Good morning. Myself Dr. Rajalakshmi, Associate Professor in Chemistry. In this session we are going to discuss about the very important topic in stereochemistry. In organic chemistry, that is stereochemistry. Stereochemistry is the branch of chemistry that deals about the three-dimensional structures of the molecule, that describes the molecular geometry of substances, their physical properties related to such geometry, the relationship in space between the different atoms and groups in your molecule during chemical reactions, and the way in which chemical equilibria and the rate of the reactions are affected by those spatial relationships. Want of and Liebel, who were called the father of chemistry, and they are the founders of chemistry. First, they were predicted the structure of tetrahedral carbon, that means sp3 hybridized carbon. In 1874, the Nobel Prize for Chemistry was given to them in 1901. Stereoisomers, they are classified into two major categories. One is conformational isomerism, another one is configurational isomerism. Conformational isomers are arising out of the momentary spatial arrangement of atoms and groups arising out of the CC single bond rotation. But the configurational isomers, they differ only in their spatial arrangement. That means the atoms and groups attached to the carbon atom that may differ in both the isomers. Configurational isomers are further classified into two types. One is aptical isomerism, another major category is geometrical isomerism. So in this session we will discuss about aptical isomerism. Aptical isomerism is the phenomenon in which isomers possesses molecular asymmetry. Solutions of certain organic compounds have the property of rotating the plane of plane polarized light. These substances are said to possess aptical activity. That means the solutions are the organic compounds which can capable of rotating the plane polarized light only can show aptical activity. If the solutions are rotating the plane polarized light towards the right, that means the clockwise direction as shown in the figure, they are said to be dextrorotatory. On the other hand, if the solutions are rotating the plane polarized light towards left, they are called as S-configured compounds, or they are called as levorotatory. What is the main criterion for a compound to show aptical activity? Means asymmetric carbon atom is the necessary condition for a compound to show optical activity. What is called asymmetric carbon atom? If a carbon atom is attached to 4 different atoms or groups, then the resulting molecule can have any elements of symmetry. That means it is said to be asymmetric. When it will be asymmetric means if the compound is attached to 4 different groups or atoms, then the compound will be devoid of all the symmetry elements. So that type of compounds are said to be asymmetric. So any molecule in which there is a single carbon atom bonded to 4 different functional groups, that means groups or atoms, there is asymmetry and the molecule is chiral. This carbon atom is sometimes called asymmetric carbon, or it is said to possess chiral center. An asymmetric center is shown in 3 dimension. Compound possessing one asymmetric center. So in this example 2-bromobutane, the 2 isomers are given here. The tetrahedral carbon can capable of existing in 2 isomeric form. So a tetrahedral carbon should capable of existing in 2 isomeric form means that can exhibit aptical activity. Condition for aptical activity, the molecule must be chiral, that means it must have 2 structures which are mirror images and cannot be superimposed on one another. Presence of asymmetric carbon atom is not sufficient to decide whether the molecule is aptically active or not. The molecule as a whole must be asymmetric. That means some of the compounds may possess 1 asymmetric carbon atom or even 2 asymmetric carbon atom, but the compound may not be aptically active. Some cases they are found to be aptically inactive. This is because the compound as a whole may not be asymmetric. So actual condition, the necessary condition for a compound to show optical activity is the compound should, that means the molecule as a whole must be asymmetric. A simple device to decide whether the molecule is symmetric or not is to ascertain whether it contains any elements of symmetry. Chirality. Any molecule which is not superimposable on its mirror image is said to possess chirality. The term chirality means having handedness. We are living in the chiral world, that means everyone is possessing at least 2 hands. So, the given figure, there were 2 hands. The 2 hands are mirror images to each other. In the second figure, if you are superimposing one hand on the other hand, they are found to be non-superimposable. So, that means the mirror images which are found to be non-superimposable. So, that is said to be handedness. In one of the hand, the right thumb is found to be, that is directed towards the right hand side. In the another hand, the thumb finger, for example, thumb finger only, okay, the thumb finger is pointing towards the left hand direction. That is the reason why the 2 are non-superimposable to each other. So, all are said to be handedness. The structure of optical isomers differ only in handedness, one being left-handed like us and the other being right-handed. The chirality is the necessary and sufficient condition for optical activity. This chirality is now equivalent to asymmetry or dissymmetry. Thus, the case of optical activity is the presence of one or more chiral center in a molecule. Some of the non-superimposable mirror images are given here. Our 2 hands and 2 ears, they are found to be mirror images to each other, but they are non-superimposable to each other. Now the 2 tetrahedral carbon containing 4 different atoms and groups are given here. Now these 2 are said to be handedness. In the first figure, the ball which is red in color or pink in color is pointing towards left hand side, and the another isomer, that is said to be the mirror image of the one, is having the ball in the right hand direction, the pink ball in the right hand direction. So, now this is said to be handedness. The one which is in the right hand is found to be left in the other isomer. So, because of this reason, the compounds are found to be non-superimposable to each other. So, this system is said to be optically active. For a compound to show optical activity, there should be completely devoid of all the symmetry element. There were several symmetry elements. Among them, we will discuss about at least 3. Number 1, plane of symmetry. A plane which divides an object into 2 identical halves is called plane of symmetry. That means a plane or a plane of symmetry divides a molecule in such a way that the atoms or groups on the one side of the plane form mirror image of those on the other side. The following molecule possesses plane of symmetry. In this case, the tartaric acid, here this is the plane that divides the molecule. This plane that divides the molecule into 2 identical halves. See, in the chiral carbon number 1, there are some groups like OH, COOH and hydrogen. In the second carbon also hydrogen, OH and COOH. Now these 2 carbons are identical to each other. Now this plane, this horizontal plane that cuts the molecule into 2 identical halves. Now the system is said to be symmetric. That means the system is said to have plane of symmetry. The compound is mesotartaric acid. Center of symmetry. A center of symmetry is a point from which lines when drawn on one side and it is produced to the same extent on the other side, you have to make identical points in the molecule. That means with respect to this center, we are moving from one direction, there we are meeting COOH. If you are extending on the same in the opposite direction, we are meeting the same group COOH. Now this system is said to be symmetric with respect to this point. Axis of symmetry. A molecule is said to possess n-fold axis of symmetry when rotated through an angle of 360 by n. Here n is the number of rotation the molecule have to takes place to attain the original configuration. So 360 by n above the axis, it produces identical configuration. If any one of the elements of symmetry is present in the molecule, then the molecule is symmetrical. Then the molecule becomes superimposable and its mirror image, so it is not optically active. For example, benzene. In that there are 6 carbon atoms, that is sp2 hybridized, all of them are symmetrical. So the benzene is symmetrical. So in order to attain the original configuration, the molecule has to be rotated for 6 times if you are rotating for 60 degree. So that compound is said to possess C6 axis of rotation. Now benzene is symmetric, that means that is found to possess axis of symmetry. Optical activity of tartaric acid, it's very interesting one. The tartaric acid that contains 2 similar asymmetric carbon atoms. In order to find out the number of isomer for a compound, we have to use the formula that is given by Vantoff and Liebel, the 2 scientists, that is 2 power n. For the compound, if there are 2 numbers of chiral carbon are found to be present, in the example given here, there were 2 chiral carbon atoms. The 2 chiral carbons are similar, but for dissimilar compounds, the formula 2 power n we have to use. 2 power 2, that is equal to 4 isomer are expected, but for this case these 2 chiral carbons are similar. See, in that case both the carbons are attached to hydrogen OH and COOH. The groups are similar, so that chiral carbons are said to be similar chiral carbon. So that the formula is slightly modified into 2 power n minus 1. So totally 3 numbers of isomers are possible. So the 3 isomers are given in the figure. Number 1, that in that case both the chiral carbons are rotating the plane polarized light towards the right hand side. So the molecule as a whole is found to be dextrorotatory. In the structure 2, that means the isomer 2, in that case both the chiral carbon atoms are rotating the plane polarized light towards left hand direction. That's why the compound is found to be levorotatory. But in the case of the third isomer, there were 2 chiral carbon atoms, still they are found to be asymmetric. In that case there is a possibility, that means if you are putting a plane there, that cuts the molecule into 2 identical halves. So the system is said to have plane of symmetry. So because of this reason, though the system is having 2 chiral center, is found to be optically inactive. That's why in the first slide itself I told possessing chiral carbon is not sufficient for a compound to show optical activity, but the molecule as a whole, like compound number 1 and compound number 2, should be asymmetric. Some of the meso compounds are given here. Enantiomers. Enantiomers are stereoisomers, or they are said to be configurational isomers. Compounds having same molecular formula with a different configuration are called stereoisomers. 2 compounds which are stereoisomers, that means configuration isomers, and are mirror images to each other, but are not non-superimposable, that are all called enantiomers. In the given example, there were 2 isomers, L-lactic acid, L plus lactic acid and D minus lactic acid. The conventional assignment is given here, L and D. The plus and minus sign that indicates the direction of rotation. Now these 2 isomers, they differ only in their handedness. Now these 2 are mirror images to each other and are not superimposable to each other. That's why these 2 isomers are said to be enantiomers. Diastereoisomers. A compound may exist in several forms with various configuration. 2 such forms may have different configuration, but they are not mirror images to each other. Such a pair is called a diastereoisomer. The diastereoisomers are again stereoisomers. They may either be optical isomers or geometrical isomer. They are not mirror images to each other. Some of the examples are given here. Number 1 and 2, the structure 1 and 2 are erythros. 3 and 4 are trios. The erythroisomers, say in the case of erythroisomers, the 1 and 2 are found to be mirror images to each other, but are not superimposable mirror images. So they are said to be enantiomers. Like that, 3 and 4, the erythro pair, that are also found to be mirror images and are non superimposable to each other. But the structure 1 and 3 are not mirror images to each other. So 1 and 2 are enantiomers, 3 and 4 are enantiomers, 1 and 3 and 1 and 4 are isomers. They differ only in their spatial arrangements, having same molecular formula, but they are not mirror images. So 1 and 3 and 1 and 4, 2 and 3 and 2 and 4 are said to be diastereoisomers. Not only optical isomers, even geometrical isomers, for example malic acid and fumaric acid, the two are said to be diastereoisomer because they also differ in their configuration only, but are not mirror images. So yeah, they are said to be again diastereoisomers. In initial days there were some convention to assign the configuration of any compound, any chiral compounds. In that case, D and L notation, as we have seen in the previous case, in the case of lactic acid, L plus lactic acid and D minus lactic acid that we have seen under the enantiomers. Here the notation L and D, that is the conventional method to denote the configuration of the compounds. Because of demerits of some demerits of this notation, then later onwards the three scientists Kahn, Ingold and Prelag, they have governed some rules and they give a new method that is called absolute configuration. The R and S configuration, that is the nomenclature used for naming enantiomers of a chiral compound. The R and S system of naming is referred to as CAP or Kahn, Ingold, Prelag system. Actually, it was proposed by Robert Kahn, Chris Ingold and Vladimir Prelag in 1966. This system is also known as the absolute configuration of chiral compounds. How to assign the configuration of a chiral compound? They have given some procedure to assign the configuration for a particular chiral compound. Let us first consider the procedure for a molecule containing one asymmetric carbon atom. The four groups are first added according to the sequence rule. The molecule is now imagined so that the group of lowest priority is directed away from our eyesight as given in the figure. The arrangement of the remaining groups is observed. If we proceed from the group of highest priority to the least one, then that is said to have R configuration, that means rectus. And then if you are moving from the group of highest priority to the next and then to the least, means then in the anti-clockwise direction, that is said to have S configuration, sinister. In Latin it is called as sinister. So just to assign the atoms and groups attached to the tetrahedral carbon atom, first they have to be arranged according to the sequence rule. What is the rule we have to follow? Rule 1, first examine the atoms directly attached to the stereocenter of the compound. An atom with a higher atomic number takes precedence over atom with a lower atomic number. Hydrogen is the low prior group because it has a lowest atomic number. The atom with higher atomic number has higher priority. In case of halogen groups, iodine comes first, then comes bromine, then comes chlorine. So many atoms and groups are given here. When comparing isotopes, atoms with a higher mass number has higher priority. For example, in the case of oxygen atom, there were two isotopes, O18 and O16. So here both of them are having same atomic number. So that what we have to do, we have to consider the mass number. So oxygen 18 that has the highest priority, then comes O16. Like that N15 and N14 there. Here we have to consider the mass number only, C13 and C12. So when isotopes are attached to an atom, means in that case we have to seek the mass number. Rule 2, if there are two or more substituents which have same element directly attached to chiral carbon, proceed along the substituent chain until a point of difference is found. Determine which of the chains has the first connection to an atom with the highest priority, the highest atomic number, the chain has the higher priority. For example, if the chiral carbon atom is attached to ethyl and methyl groups, in that case ethyl has the higher priority, then comes methyl. Why? Means in case of methyl there were 3 hydrogen atoms attached to the carbon which is attached to the stereogenic center, but in case of ethyl the carbon which is attached to the stereo center is attached to hydrogen and one more carbon atom. So that's why that ethyl group has the highest priority than methyl group. Rule 3. For assigning priority, multiple bonds are treated as if each bond of the multiple bond is bonded to a unique atom. That means C double bond C, a ethylene molecule is there, means the C that is considered as the duplicate of that one. That means the carbon atom is double time bonded to carbon. C singly bonded to one carbon, and again the same C is bonded to another carbon, that is called duplicate. Suppose if it is triply bonded to a carbon atom or some other heteroatom, means that atom is considered as a triplicate of that one. So in that case acetylene comes first, then comes ethylene. The carbon of an aldehyde substituent is treated as if it is bonded to a hydrogen and 2 oxygen atom. So that aldehyde is prioritized as given here. Let's see how to assign the configuration of a compound after arranging the atoms and groups attached to the stereo center, that means chiral carbon atom, according to the sequence rule. Here so this carbon atom that is attached to OH, Br, CH3 and a hydrogen atom. In that bromine is the atom having highest priority. So label this as 1, and OH is the next atom having higher atomic number. So label that as 2, and then comes the methyl group. That means the carbon is attached to the stereogenic center. So this as the number is 3. The atom of least priority is in the left hand side, hydrogen. Now we have to bring down the atom of least priority to the bottom, so that it is assumed that the group of least priority is far away from our eyesight. So for that we have to bring down. So in order to bring the atom in the left hand side to the bottom, we have to make one interconversion like this. So after making one interconversion, we will get a new compound that may not have the identical configuration of the original one. So in order to attain or regain the original configuration, we should take the mirror image of that compound. So after taking the mirror image of that one, we will get a compound that will have the configuration of our starting compound, this one. Now in this case the bromine has the highest priority, 1, 2, 3. Now we have to move from the atom of highest priority to the least. In which direction we are moving? In the anti-clockwise direction. So what is the configuration now? It is S. But in the example 2, the group of least priority is in the top. So in order to bring the group to the bottom, we have to make some interconversion. When we are making some interconversion, in the first interconversion the group will come to the left hand side. Now we have to bring down the group to the bottom. For that you have to make another interconversion. In this case the group is in the bottom. Now this is having the highest priority, OH is having the highest priority, then comes amino group, and then comes carboxylic acid group. Now we have to move from the group of highest priority to the second prior group and then to the third prior group. So this is also in the anti-clockwise direction. So the configuration now is yes. So if you are making only one interconversion, you have to take the mirror image to regain the original configuration. If you are taking two interconversion to bring down the group of least priority to the bottom, we have to no need to take mirror image. Okay. So at that time you can assign the configuration. Now the configuration of this compound is found to be yes. Hope you might be benefited from this session. The rest we will discuss in another session. Thank you.